So, hello and welcome back. So in this video, basically in the previous videos, we have been talking about permutation. Now in this video, we want to talk about combination. So combination is not very different from permutation. It's well, but it's well, of course, it's a little bit different. So combination, what that is that basically, for example, assume that there is a group of three, let's say that there is a group of three tennis players. There's a group of three tennis players. You have three people over. Oh, basically, you have three people, and a team consisting of two players, and a team consisting of two players is to be formed from among these three people. So basically, you have three people and a team consisting of two players is to be formed from among these three people. In how many ways can you do that? So suppose that for example the three players are, for example, X, Y and Z. These are the players. So of course you know that when you want to select a team of two players, it doesn't, for example, if you pick the person X with person Y, and then you can pick also person X with person Z. You can also pick person Y with person Z. You can also so X with Y, X with Z, Y with X, Y with Z, and of course you can pick Z with X as well. Z with X as well. So as you can see, there are four ways of doing that. But then in this process, for example, you picked X with Y. Of course, you can pick Y with X as well, meaning that you can write Y with X as well. And of course, the only difference there is between these two pairs is that the order here is different. Here you've picked X with Y. Here you've picked Y with X. But at the end of the day, since it is a team, X is playing with Y, and again here the same thing. X is playing with Y, or you can say that Y is playing with X, which is the same thing. So in cases where the order is not important, for example, in such cases where the order is not important, what we do is that we just simply forget about all of these different ways of selecting the same objects in different orders, right? Meaning that, for example, if I were to, for example, if I were to ask you, for example, what is all the permutations of x and y? So you have x and y over here, and all of the permutations of x and y would be, as you know, 2 factorial, right? So that, which is equal to 2. So that means that there are 2 ways of rearranging the letters x and y, and then you would get x comma y, you would get y comma x. But then these two different basically permutations are basically the same 2 members playing against one another or competing against one another. So it doesn't really matter whether you write x with y or whether you write y with x. At the end of the day, the same 2 people are basically playing against one another. So that means that this is unnecessary information that I just don't need to write. And so what that means is that in such cases where basically the order does not matter, you just simply forget about all the permutations related to each of the choices that you make, and then just simply write your results in this simple way, meaning that either, very simple language, you want to pick a group of you want to pick teams of 2 players out of 3 people. So either you can pick the first person with the second person, or the first person with the third person, or the second person with the third person, or the third person with the first person, and that's all the possible ways that you can do it. Other than that, it's not possible. Again, it's possible that, for example, here you've picked, for example, y with z, meaning that the second person with the third person, you could argue that, okay, so I can also pick the third person with the second person, meaning that pick z comma y. But then again here, what happens is that y with z are basically 2 particular persons, and again over here the same 2 particular persons have been selected, so it makes no sense to do that. So if basically you consider all the ways of rearranging, for example, n objects, and taking, for example, r of those objects at a time, and then if you don't care about the order, if the order doesn't matter to you, so what you can do is that the only thing that you care about is selecting those people together. Then of course you can forget completely about the order, and so relative to that you're going to lose a whole lot of basically results, but then you will get a bunch of results in which particular basically members of the group that we call n basically are going to be selected together, and this concept we call it basically combination. Now it seems that there is in fact there are only 3 possible ways in which a team could be constructed. We could construct the team as x comma y, y comma z. It seems that I've made a mistake here. X comma y is one way of doing so. Y comma z is another way of doing so, for example here. And then there is x comma z. That's actually the same thing. You see over here, I have made a mistake. That's not possible. So there is actually only 3 ways of doing that. So x comma z. So now in this, basically in this particular example that we talked about, each of these selections, basically each selection, or you can say each such selection, is called a combination. Is called a combination. And to be more exact, it's called a combination of 3 different objects. Here you have basically, here you have 3 objects, or you could say 3 different objects. So then each of these selections is called, basically, is called a combination of 3 different objects. A combination of a combination of 3 different objects. 3 different objects taken 2 at a time. So each of these selections, to be more specific, is called a combination of 3 different objects taken 2 at a time. And of course, as we mentioned before, in combination, or in a combination, order is not important. Order is not important. Now let's see a couple more examples here. Let's see a couple more examples. Okay, so now let's have a couple more examples here. So suppose that there are, for example, 12 people in a room who meet and shake hands. How do you determine, for example, the number of handshakes that take place between those people? So if you think about this situation, for example, as you have person 1, you have person 2, you have person 3, and so on and so forth, all the way up to person 12. So of course you know that basically person 1 shakes hands with person 2, right? And also what happens is person 2 is also shaking hands with person 1. Person 2 is also shaking hands with person 1. So these are, I mean, as far as shaking hands is concerned, person 1 shaking hands with person 2, or person 2 shaking hands with person 1, are not 2 different events, because the same 2 people have shaken hands. And our goal here is to count the number of handshakes, and we are not concerned about the fact that whether person 1 has shaken hands with person 2, or person 2 has shaken hands with person 1, or I mean which one has done it first, which one has done it second. That's not important here. So again, the order in this, for example, in this particular situation, the order of these pairs does not really matter. All that really matters here is that when you make a selection here, for example, a selection being, for example, person 1 and person 2, all that matters is that basically this selection conveys the information that person 1 and person 2, these two people have shaken hands, and of course, again, here order does not matter at all. It doesn't matter. Basically, it doesn't matter because there is no order really. So what that means is that, for example, this is another typical situation where basically the concept of combination comes in. And of course, you can pick, for example, person 1 with person 3. You can pick, for example, person 1 with person 4. Person 1 with person 4. And so on and so forth. And you would get a bunch of such selections. So what happens here is that so each of these selections, each of such selections, I could call them the combination of two different, for example, objects, taken, I'm sorry, not two different objects. I can call this a combination of 12 different objects, taken two at a time. So again, here, basically X shaking hands with Y and Y with X will not be different handshakes. They are the same handshakes, the same two people. And of course here the order is not important. So there will be as many handshakes as there are combinations of 12 different things taken two at a time. There we can have other examples as well. For example, the number of points, or basically you could say that, for example, 7 points lie on a circle, and so on and so forth, but I suppose you get the idea. Now, in order to obtain the formula, for finding the number of combinations of n different objects taken R at a time, what we do is basically we can use permutation in order to find some formula for combination. Now, so now what we want to do is we obtain the formula for finding the number of combinations, of n different objects n different objects taken r at a time, and we denote that by n combination r. So now let's see how we can find that formula, and to give you a heads up, we are going to we already know the formula for permutation. We know that n permutation r is equal to n factorial over n minus r factorial. We already know that. We know that already. So we can use this formula. This is the formula for permutation. So we can use this formula in order to decide that. Okay, so now let's see how we can find the formula for combination. Now suppose that we have 4 different objects, for example A, B, C, and D. Suppose that we have 4. Actually 4, I should write it this way. 4 different objects. I'm talking about different objects. We need to pay attention to that, of course, because it's important. 4 different objects, meaning that the results would be different, of course, if the objects were not different. So suppose that we have 4 different objects, A, B, C, and D. A, B, C, and D. Taking 2 at a time, taking these objects 2 at a time, if you have to make combinations, these will be, so taking 2 at a time, you have these objects A, B, C, and D. So taking 2 at a time, you would have basically A with B, A with C, A with C, A with D. Then you have, again, you can see that I could choose, for example, B with A, but that would be the same combination because I have already chosen A with B, and B with A would be the same 2 objects. Or B with C, or B with D. Now, again, you can see that I can choose A with C with A, but I have already done that. C with B, I have already done that. C with D, I have not done that. And then you can see that I can choose A with D, which I have already done. D with B, which I have already done. D with C, which I have already done. So that's all the possible combinations of these 4 objects. So that's 1, 2, 3, 4, 5, and 6. Basically, that is 6 combinations. That is 6 combinations. 6 combinations of 4 different objects. Taken 2 at a time. And that's all the possible combinations, by the way. So these are all the possible combinations. So we have basically, and for example here you can see that if I write, for example, AB, and also basically in the process you could choose, for example, BA as well, they are the same combinations. These two are the same combinations, as order does not matter. As order does not matter. And meaning that order would not alter the combination. Would not alter the combination. Order would not alter the combination, meaning that, so A and B, basically this is a combination of object A and B. And BA, this is again a combination of the object B and A, or you could say a combination of the object A and B. And of course, I know that the order is different between these two pairs. But as we said here, order would not alter the combination, meaning that when you change the order, it doesn't make it a different combination. It's still the exact same combination. As far as basically combination definition wise is concerned, the combination has not changed. Okay, so for the same reason, we have, as you paid attention to the process where we got these combinations, I had to I chose not to write many certain things over here, because I said that, okay, so I have already written this, I have already written that, I have already written that, and so on and so forth, and we came up only with these 6 basically combinations. Otherwise I would have come up with probably a lot more, probably over 12 or so, way over 12 basically different selections here. So here you can say that there are as many as 6 combinations of 4 different objects taken 2 at a time. Which means that, since I know this basically, that means that basically the combination, since I know that basically combination of 4 different objects taken 2 at a time, of course we said that that's denoted by 4 combination 2. And now we know that 4 combination 2 is actually equal to 6, right? Okay, so now what happens is that, what we found out was that basically 4 combination 2 is equal to 6, as we saw in this simple experiment. 4 combination 2 is equal to 6. Now, corresponding to each combination in the list, we can arrive at two factorial permutations. And if you want to basically verify that, you can of course do that, because as you can see, if I have the same objects A, B, C, and D, I have the same objects A, B, C, and D, and let's list all of the different basically selections of these four different objects. And this time, let's not take into consideration the order. Okay, so for example, I'm going to take A with B. I'm going to take A with C. I'm going to take A with D. So there I have three selections. Then I'm going to start with B and take B with A. Then I'm going to take B with C, right? So B with C. So then I'm going to take B with D. Then I'm going to take C with A. Then I'm going to take C with B. C with B. Then I'm going to take C with D. So C with D, I don't have it really. C with D. Then I can start with D, and then I have D with A, which is DA. Then I have D with B, which is DB. Then I have D with C, which is DC. So as you can see, over here, I have the same number of combinations. A with B, A with C, A with D, BC, BD, and CD. And I suppose over here we had 6 combinations, which are these combinations. But corresponding to basically the important thing that you can notice here is that basically corresponding to each combination, in the list, we arrive at 2 factorial permutations. We arrive at 2 factorial permutations. And 2 factorial permutations, as 2 objects in each combination can be arranged in 2 factorial ways. As 2 objects as 2 objects in each combination can be arranged in 2 factorial ways. So as you can see, for example, I have 2 objects here, A and B, and of course, if you want to calculate the permutations of 2 objects taken 2 at a time, that would be 2 permutation 2, which is equal to basically 2 factorial over 2 minus 2 factorial, which is equal to 2 factorial. Again, I have 2 objects over here. Again, 2 factorial permutations here, 2 factorial permutations here, and so on and so forth. So that means that basically corresponding to each combination, which is basically nothing but a combination of 2 objects, we arrive at 2 factorial permutations, as 2 objects in each combination can be arranged in 2 factorial ways. It's very clear here, and you can see it. Hence the number of permutations, so since basically each combination corresponds to each combination corresponds to 2 factorial permutations, then you can say that the number of permutations is 2 factorial times the number of combinations. So then you can say that hence the number of permutations, hence the number of permutations is equal to basically 4 combination 2, which is basically all of each of so basically if you calculate 4 combination 2 or we can think of this in a different way. What we can do is that these are all the permutations of these objects, right? So I can call all of these objects as basically the number of these objects over here. I can call it basically 4 permutation 2. 4 permutation 2. And 4 permutation 2 is the same thing as if I call each of these a combination of the 4 objects taken 2 at a time. That's the same thing as 4 combination 2, and then I have to divide that by, because the number of permutations is clearly basically some number times the number of permutations is clearly some number times times the number of combinations, because each of these would be a combination. Each of these items would be a combination of one possible combination of basically 4 objects taken 2 at a time, right? So I can write 4 combination 2, right? And relative to each of these combinations, I have 2 factorial permutations. So then basically I can say 2 factorial is equal to 2. So 2 factorial permutations, I can write it as 2 factorial, right? So that means that 4 permutation 2 is the same thing as 4 combination 2 times 2 factorial. Or I can say that basically 4 combination 2 is the same thing as 4 permutation 2 divided by 2 factorial, which is the same thing as basically, you know what 4 n permutation r is equal to n factorial over n minus r factorial, which is the same thing as 4 factorial over 4 minus 2 factorial divided by 2 factorial. So that means that 4 combination 2 is the same thing as 4 factorial divided by 4 minus 2 factorial times 2 factorial. Now let's suppose that, for example, this time let's suppose that we have 5 different objects. And let's suppose that we have 5 different objects, and the objects are A, B, C, D, and E. So I have 5 different objects here. Now if I take 3 at a time, if we have to make combinations, now again what I'm going to do is that I'm going to take all the different permutations of these of these different objects taken 3 at a time. We will take all the different permutations of basically 5 different objects taken 3 at a time. So what we will arrive at is basically, I can take, for example, it's a little bit more complicated than the previous case, but we can do it, of course. So I will take this, I will take A with B, and I will take A with B, and of course it's a lengthy process. But let's see if we can do it. Let's try it. And of course it's going to be a very lengthy process, meaning that, for example, you have to take A with B and then start with A and then go for B and then take each of these combinations, meaning that you would take, for example, A with B and then with C, and then you have A, B, D, and then you have A, B, E, and so now this round is over. Then you take A with C and then take the other three, meaning that A with basically AC, ACB, for example, and ACD, for example, ACD, for example, and ACE, for example, ACE. And then you have ADB, you have ADB, you have ADC, ADC, and you have ADE. And you have ADE. And you have AEB, and you have AEB, and you have AEC, and you have AED. And then you need to start with, for example, you can do the same thing with, you can start the same thing with B. You see that basically all of the permutations that I have gotten here, I have started with A, and then I have switched the second letter over here, meaning that I have started with B, and then I've gone over to C, then gone over to D, and then and so on and so forth to E. So I'm going to do the same thing here, meaning that I'm going to start with B and then go over to B and then go over to C and D and E and so on and so forth. So then I'm going to take BAC. So I'm going to take BAC. I'm going to take BAD. I'm going to take BAD. I'm going to take BAE. I'm going to take BAE, and now this round is over. So now I can switch the middle letter here, as I basically instead of A, I'm going to take C here. So BCA. So BCA and BCD and BCE. BCD. So BCD, we don't have it here. BCD and BCE. And BCE. And then I'm going to switch to basically D. So BDA. So BDA. and then I have BDA, BDC. So BDC is, you can put it somewhere over here, BDC, and BDE. And that you can also put somewhere over here. And then you can take B with, so we have taken B with A, B with C, B with D, and B with E. So BEA, and BEC. So BEC, and then BED. Which this one actually comes over here. So BEC, right? BEC and BED. So BED comes over here. Now I'm not going to do all of these, and of course you need to start with C, start with D, start with E, and so on and so forth. But what will happen over here is that, of course, I've never actually tried this, but basically based on the text that I'm reading here, and I do trust the text that I read over here, I've never actually seen any sort of mistakes in this text, or anything illogical for that matter. So then we can say that in this particular situation, so you can see that, for example, ABC, ACB, BAC, BCA, and so on and so forth. So these are all, you can say that basically, of course, the order has been changed, but it's basically the same combination. Meaning that you have the same three objects over here, ABC, 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 and so on and so forth. So then what you can say, if you keep doing the same experiment over and over again, what happens is that corresponding to each of these 5 combinations, there are 3 factorial permutations. And 3 factorial means basically 6 permutations, meaning that if you keep doing the same thing, for example, all the permutations related to the 3 letters, for example, A, B, and C, would be 6 permutations here. There are six different ways of switching or rearranging these letters, and then you would get all the different permutations of the letters A, B, and C. Okay. Now, what that means is that now the sentence that we have here, that is the important one, and that is corresponding to each of these 5 combination 3 combinations. So each of these is one 5 combination 3 combination. 5 combination 3 combination, meaning that each of, whether you take this one or this one or this one and so on and so forth, this is one combination of 5 different objects taking 3 at a time, right? So each of these objects, or each of these basically results, I can call it one 5 combination 3 combination. And if we keep doing the same experiment, all of the results that contain basically A, B, and C, which would be, for example, 1 5 combination 3 combination, the number of each of those would be 6, which is basically the same thing as 3 factorial. And so you can say that corresponding to to each of these 5 combination 3 combinations, there are 3 factorial permutations. That's the important thing here. That is the important thing here. And it says that corresponding to each of these 5 combination 3 combinations, there are 3 factorial permutations. There are 3 factorial permutations because the 3 objects in each combination, and the reason is very, very, very clear, because the 3 objects in each combination, the 3 objects in each combination can be rearranged in 3 factorial ways. And of course that's easy to understand, because if you have 3 objects, 3 different distinct objects in a, for example, over here, if you have A, B, and C, the number of basically the number of possible permutations of A, B, and C is basically 3 factorial, because you have 3 different objects and you're taking all at a time, so that's 3 permutation 3. 3 permutation 3 is simply equal to 3 factorial. We have already seen that. So we can already say that, with 100% certainty say that even without doing the experiment, we can say that corresponding to each of these 5 combination 3 combinations, there are 3 factorial permutations, because the 3 objects in each combination can be rearranged in 3 factorial ways. And so what that means is that basically all of these results that you get over here is just one permutation of that I can call 5 permutation 3. Now, corresponding to each of these permutations, there are 3 factorial permutations, or I could say each of these I could call basically a combination of the 3 letters. So I could say that basically 5 combination, meaning that basically the number of all of these basically results over here that you can denote with 5 permutation 3. Excuse me. So the number of all those different results over there you can denote with 5 permutation 3. And based on what you saw over here, you know that 5 permutation 3 is the same thing as 5 combination 3 times 3 factorial. Because suppose that, for example, you have 3 factorial such permutations here, you have 3 factorial such permutations here, you have 3 factorial such permutations, and so on and so forth. So then what that means is that 5 combination tree times 3 factorial is equal to 5 permutation tree. So 5 permutation tree is equal to 5 combination tree times 3 factorial. And so what that means is that 5 combination tree is the same thing as basically if I divide both sides of this equation, for example, by 5 permutation tree, divided by 5 permutation tree, I'll get 5 combination tree times 3 factorial over 5. Of course, well, I don't have to really do that right now, because I know the value of 5 permutation tree. 5 permutation tree is 5 factorial divided by 5 minus 3 factorial. And that is equal to 5 combination tree times 3 factorial. So that means that basically 5 combination tree is the same thing as this divided by this, right? Or you can say that to get rid of this 3 factorial, I divide both sides of this equation by 3 factorial. Meaning that if I divide both sides of this equation by 3 factorial, I'll get 5 factorial divided by 5 minus 3 factorial times 3 factorial is the same thing as 5 combination 3 times 3 factorial over 3 factorial, and so these two you can cancel out, and so you will get 5 combination 3 is the same thing as 5 factorial divided by 5 minus 3 factorial over times 3 factorial, right? So that's basically what we got here. So what we got was that 5 combination 3 is the same thing as 5 factorial divided by 5 minus 3 factorial times 5 times 3 factorial. And over here what we got was that basically 4 combination 2 is the same thing as 4 factorial over 4 minus 2 factorial times 2 factorial. So based on these two, what I can say is that it seems that this formula is basically the relationship, the formula for n combination r can be written as n factorial over n minus r factorial times r factorial. That seems to be the case. This actually seems to be the case. Now, what that means is that these examples suggest that the relationship between permutation and combination is that, or you can say that basically n permutation r is the same thing as n combination r times r factorial. You can say that because over here, for example, each of these is a permutation. So, and you can see that the number of permutation is too many, and the number of combinations is just one. For example, in the case of this column over here, you have only one combination, because over here you have the combination of the letters A, B, and C. So all of these are one combination. So then you can say that n permutation r is the same thing as n combination r times some number, and that number happens to be r factorial. So we can say that basically n permutation r is the same thing as n combination r times some number which happens to be r factorial. And of course, at this point we know that 0 is less than r, less than or equal to n. It seems that r cannot be equal to 0, but this seems to be the case here. And of course, if I in this relationship, if I were to calculate n combination r, I would simply take n permutation r and divide it by r factorial, as you already know. So what I would do, I would take this. So it seems that basically, since this is the case, so I would take n combination r and write it as basically n permutation r divided by r factorial. Now, you know that n permutation r is n factorial over n minus r factorial. We have already established that. Divided by r factorial. So that means that n combination r is the same thing as n factorial divided by n minus r factorial times r factorial. And that's basically what I have written over here. So this seems to be the case. Now let's see if we can prove this. If we can prove it, that means that it's going to be true all the time. And then we can use it in our calculations. And you might be surprised to know that basically this simple formula, of course this is in no way a simple formula, seems to be a simple formula, but you can do magical things using this formula. Basically, formulas are basically magical things, because in a formula you have algebra, and algebra is actually a magical thing. It works in magical and very, very mysterious ways. But anyway, you might be surprised to know that this little formula, it's taken human beings around over 2,000 years to find this formula. 2,000 years. And many different mathematicians all throughout the time, in over 2,000 years, it's taken them over 2,000 years to come up with this seemingly simple formula. But well, it's pretty powerful. I'm going to say, really. Now in the next video, let's prove this formula, and then we will be able to use it in our calculations. So I'll see you in the next video, and thank you.